Yes, good evening, members. I would love to welcome you back again for our edition of discussion. Today's edition will be on quantum mechanics 2. We're looking at the solutions of Schrodinger's equation. And I would love to note that there are quite a number of steps, quite a number of methods for solving Schrodinger's equation. And today we only would like to look at a few. And we know of variational method and approximation method and other methods that you might come across in your research. Today, we are yet to present approximation method. And in approximation method, we have three scenarios. One of the scenarios is when there is no opposition, and that is at zero potential, when such a particle is in a box. That is called particle in a box. That is where it experiences limited potential difference at such a point here, as you can see. That is to say, in this other part which is a greenish part, the particle experience as much potential difference as possible. And then in this region, in this loop of 0 to A, we don't have potential barrier on that point. And the second case is when we have a step up potential. This is in the point of a potential Vx equals to V naught, when we have a potential at a certain point. And then the third point is when we have a barrier, potential barrier within a particular range of like from negative A to A. Such is one of the analyses we are going to do today. And to start it off, we click on the first analysis, which is on a case. The first case is a case of potential at zero. That is particle in a box. We always refer to as analysis of a particle in a box as of this case. Members, I am glad to tell you that Schrodinger's equation has some methods, just like I told you. We talk of variational method, and then we talk of approximation method. For us, we are taking today approximation methods, and the first case, we said we're taking the first case of we talked of these cases in the introductory part, where we have a zero potential, and then a potential at a step up, and then a potential barrier, of which it is given a potential within a particular range, which is from a negative to a positive value, or negative to a negative, given just such a range, okay? That is when the particle experiences potential barrier within a particular limit. Now, the Schrodinger's equation is written as this. You can see in your derivation, you got your Schrodinger's equation as this. But now, how do we solve this for the case of all these positions? So we are taking the first case today, where we have potential V equals to zero. There's no potential that. So at zero potential, this is a case of free particle that does not experience potential barriers in that given interval of like from 0 to A, just like we started from the first part. Now, at this junction, you will agree with me that the Schrodinger's equation will be written as this, because the potential barrier part is now 0, and this potential barrier being 0, we rewrite it this, and when we rearrange, then we shall have it as d2 function. This is our wave function, which is d2 psi out of dx squared. The second derivative is equals to the negative of this, which is equals to that. And we are taking a case. Now let us say we take a case of a constant. Let us say our k, constant k, is given as root of 2me divided by h cross. Then we consider the square of k will give us k squared equals to 2me h cross. Now, in such a case, when we substitute back, we shall have harmonic equation here. We shall have a harmonic equation, as we may also believe the fact that this particle in the box will be behaving as harmonic form. So this is the equation, the harmonic form. And of course, this harmonic equation has a solution of psi equals to a sine kx plus b cos kx, as you may prior in other courses you'll be getting. Next, we have we have that at these junctures, at this point of limits at zero, the wave function is also zero because it is continuous. We consider the wave function to be continuous at the limit as well. Rather, in the box, there is no what? There is no, this is our box. There is no wave potential there, potential difference. I mean, potential within that, I mean, the particle will not experience a potential at that point, meaning if it is continuous, therefore at the boundary also, our wave function is zero to give us a zero potential as well. And then at the upper boundary as well, it is a zero. Therefore, we can see that it is psi x at x equals to 0 is equals to psi x at x equals to a, which is equals to a 0. Now, if psi x at x equals to a is equals to a 0, thus we have that a sine of 0 equals to plus b cos of 0 equals to 0, and this will give us b equals to a 0. If you can see that, then b equals to 0 is our value. So we find that b equals to 0, and we can now rewrite our value. Can now rewrite our value as psi x equals to a sine kx, of which we are solving for a. For x equals to a also is equals to 0. Therefore, a cannot be a 0. For mathematics, we say either of these two functions, either a or sine of ka has to be 0. Therefore, if a cannot be 0, then sine of ka has to be 0. Therefore, giving this, we have that ka equals to sine inverse of 0, which is n pi. You know that n integer angle of pi, the sine of that integer is 0. Therefore, k is written as n pi out of a, of which when we substitute k, then we shall have it as n pi over a x. Now we have to normalize this, and our first and other condition is that this wave function given by psi x has to be normalized. To normalize the wave function, we can see that we normalize it with this bra and ket, which is the inner product of the function has to be 1. Therefore, the summation from the lower limit to the upper limit of this inner function has to be, the inner product of the function has to be 1. Therefore, when we substitute, but we know that this one, psi x is not what? Is not a complex number. Therefore, since it is not a complex number, the conjugate is equals to the real number, the real function given. Therefore, since it is a real number, then psi star is equal to psi. Therefore, is equal to ax. I mean, a sine of n pi x. Therefore, its multiplication of psi star times psi is just a square of a sine, just like you can see this. So integrating from 0 to a of a square of this will give us a 1 to normalize this function. And now we can see that when we are normalizing this function, we have a result of a squared integrating of this squared now equals to 1, of which we use a substitution, a double angle substitution of sine squared. This is an identity of sine squared a equals to 1 minus cos 2a divided by 2. Therefore, when we substitute there, you can see that it is an integration of, a squared integral from 0 to a, which is of course this, then it gives us a 1. That is by principle of the normalization. Therefore, when we work out the mathematics, we can find that we first integrate the angle. And then we substitute. Now, when we integrate, the integration here, we have to check on the integration because we divide by the reciprocal of the derivative of the angle. Therefore, this one has to be a out of 2n pi. A out of 2n pi. So then we substitute, and then we get our value. Now, in getting the value, we can see that what is surviving when we substitute a here. What is surviving when we substitute a here is x. So we shall have a squared a divided by 2 equals to 1, and then we have a squared equals to 2 over a. Therefore, we have our a as root of 2 over a. Therefore, our psi can be written as root of 2 over a. Now, I will employ you to go and do the integration here thoroughly as my fellow colleagues. You go and do this integration well, but then we shall have to realize that our a is given as root of 2 over a. Now, by that, we can rewrite now our solution to the Schrodinger's equation. Our first solution is psi nx equals to root of 2a sine of n pi a by x. Now, therefore, we now have to now write our k. Remember that we said k equals to n pi over a. If k is equals to n pi over a, then the square was given as k squared to me x, h cross here, given here. Now, we cited that to be our value of k as a constant. Therefore, when we replace, because we found that k is n pi over a, then we replace by that. Therefore, we shall have the energy, the nth energy, energy level. The nth energy level is given by h cross squared pi out of 2ma squared n squared. Okay, that is the nth energy level. Of course, this n is an integer greater than 0. Is an integer of a positive. It is always positive. Therefore, we can rewrite now this as that, the solution to the Schrodinger's equation, giving us energy En as the other. So we have points also to note here. And this point is that this is known as the problem. First of all, we know that this condition here, we are talking of a problem in a box when like one is stuck within a wall. A particle is stuck within a wall. The second recognition is that the wave function must be continuous even over the boundaries of the lower limit and then the upper limit. Then secondly, thirdly, the wave function must be normalized. To normalize is that we are to ensure that the probability of finding the particle within the boundary is not greater than 1. That is the benefit of normalizing this function. So when we normalize it, we find that it is easy to find the particle within such a box. So if we confirm that the probability of getting the particle within the box is 1, therefore we are good to go. So if these three conditions are catered for, then we can realize that we have this. Then we can realize that we have this. We have this solution now taken care of. This one, and then giving us the what? Giving us the energy value there. Yeah, so that is the point where I wanted to emphasize most. Now, next as we go, we need to also analyze the results. One of the analysis of the results is the orthogonality of the solution set. We are well aware that these values gives us different. Okay, because we said n, because we said n is. We said n is just an integer greater than 0. Integer is greater than 0, meaning they are positive. So we have n1, n2, n3, n4. So this one gives us different values. But now, which means they are of different function. How about their orthogonality? Orthogonal means the inner product has to be either 0 or 1. That is to say, for n equals to m is giving us what? A 1. And then for n not equals to m, if n is not equals to m, then it is a 0. This is what we call the Kronecker delta. This Kronecker delta is just the inner product of the functions at different energy levels, like n and m. So for us to prove this, we need to also determine that for n equals to m, the Kronecker delta, that is the inner product, the inner product of these wave functions gives us a 1. But for n not equals to m, if n is not equals to m, then the Kronecker delta is given as a 0. So today, I would love that we empower ourselves and we work on to a given equation here. Now, supposing we are given a question like this, given that the wave function psi n of x equals to root of 2 over n sine of n pi a by x is a solution to the Schrodinger's equation, then we are provided to prove that the notion Kronecker delta equals to 0 stands for n not equals to 1 and n equals to 1 for this. This question is just the same as the lower question. This is just a different way of setting the same question. We can even say, prove that the wave function psi n is equals to this is orthogonal, meaning these two conditions are for orthogonality. These two conditions here are for orthogonality. So when n is not equals to m, the Kronecker delta has to be a 0. When n is equals to m, then the Kronecker delta has to be 1. Therefore, in this case, let us today check at the case of n not equals to m. Then at the last point, I shall ask you to determine for n equals to m. So today we are talking of n not equals to m. My assignment here is coming n equals to m. So now when we use n equals to n, when we use this given wave function, therefore, for the next energy level or the next function will be psi of m, where we shall have a change only in the m here. Therefore, the inner product of psi n and psi m will be this other one, which is giving us the Kronecker delta. Now, if this is the Kronecker delta, then this one giving us the Kronecker delta is now, if this is now the Kronecker delta, then we know that the Kronecker delta is the integration, is the inner product of this case. Therefore, we substitute them, and we have the inner product of psi n and psi m is given as 2 over, because we have this root of 2 over a times root of 2 over a gives us a 2 over a. So we have integration from this to that, then we substitute for this. Now we need to use an identity here. Now we are using this identity, sine of 2 sine of phi, okay, sine of theta, sine of phi is equals to cos of the difference minus cos of the summation of the angles into play. Therefore, if our angle here is given as what? Let me pick up a pen. If our angle, at this case, our angle is theta and then phi, our angle is theta and phi, then the difference, cos of the difference minus cos of the, this is just an identity we are all familiar with. Therefore, it is going to help us into play. Let us say our theta is the first angle here, and is the first angle of n, and then our psi is the second angle of m. Now, in this case, now we have that, we employ that, and then we come the difference, and then the summation here, okay? N pi over a x minus m pi over ax, then minus cos of n pi over ax plus m pi over ax. Therefore, we factorize pi over ax, and here also we factorize pi over ax, then we shall be left with, but remember this one is a 2, we are seeing a 2 here, so our single part here is giving us a division by 2, so that afterwards when we are substituting down here, is going to be a substitution, then that 2 will cancel 1 over a, and then we are left with a 1 over a, and you can see that in the second case here, the substitution, okay, the integration, this can now be integrated because it is cos of a certain angle, and we employ the property of integration, like when we have subtraction plus or minus here, then we can now integrate them piece by piece, piecewise integration now here. Now, when we integrate, there need to be 1 over a here. 1 over a has to be in here. Now, if this is 1 over a, then we have the integration, because when we integrate a cos, we get a negative sign. So the negative is changing this negative here, because we integrate even we differentiate the angle, then we have it down here. Do the integration, And then we shall find that this one displayed on the screen is the integration, of which later on, when we substitute the upper limit, which is a, we shall have n minus m pi plus sine of, okay, sine of n minus m pi plus sine of n minus m pi, which is, of course, these are integers. Difference of integers will remain integers. Difference of integers will, I mean, summation of integers will also remain integers. So any integer multiple of a pi gives us a sign of 0. Therefore, it is a 0 plus a 0. And also when we substitute a 0 as the lower limit here, now we substitute 0 here, we shall have sign of 0 plus sign of 0, which is also 0 plus a 0. You can bear me witness that this one here is giving us a summation of 0, and therefore you can find that, we can see clearly that what? The Kronecker delta is a 0 as prior given. But now our assignment is here. Prove it that the Kronecker delta nm is equal to 0 for n equals to m. Thank you for listening to me and attentively paying a concern. In the link below my YouTube channel, do this assignment, submit, and I receive your comment. As fellows from Uganda Matters, I will also expect submission. Thank you. See you as you connect to my YouTube channel. Thank you. I believe by this presentation, you shall be good to go. All right.
You have a YouTube channel.